طيب السلام عليكم يا شباب. So we are continuing with the second lecture and the last one on antennas and propagation. Remember, for the previous lecture, we were actually looking at how you can figure out when you do an analysis of an antenna, what do you need to figure out? So the analysis typically tries to seek an expression for the vector of the electric field and the vector of the magnetic field everywhere around the antenna. We found that the best geometric coordinate to use in this case is the spherical coordinate. We refer everything to the center of the antenna itself. We did the analysis. You don't really need to do the electromagnetic analysis or anything, but just to understand that when we did that analysis, we did it for something called the far field, because that's more important for us when we deal with communication system. It means that we are trying to look at the electric and the magnetic field and the characteristics of the antenna when the receiver is multiple wavelengths away from the transmitter. So they are not very close to each other. And accordingly, we can use the far field approximation. We started with some kind of a theoretical antenna called the Hertzian dipole, very short dipole antenna. And very short here means that the length of that antenna is much smaller than the wavelength of the signal. It's easier to analyze this small one, and then we use it to figure out the analysis for a more practical dimension wise antenna. So regardless of the details of the analysis, we found that the electric field is typically, if you are dealing with spherical coordinates centered at the center of the antenna. So we found that, I'll try to draw something here. So if this is your antenna, and this point in the middle is the center of the antenna, then we found that if you are looking for the electric field at this point, for example, this electric field is going to be in the direction of theta. So at this particular point that I picked, if I somehow connect this to the center, and I will use another color. So if this is my angle theta from the z-axis, the electric field at this point is going to be pointing. Sorry. How do I do a undo? There's no undo here. No. Okay. Anyways, it should be, if I want to draw it correctly, it should be something like this. So the electric field is going to be in this direction, which is the direction of theta. Now, if I go to another angle, it will be in this direction, right? It's always in the direction of theta, which is perpendicular to this line coming from here, right? So that's the direction of my electric field. And we found that the magnetic field is typically in the direction of phi, the azimuth angle. So if in the front here, it will be this way. If I go a little bit around, it will be this way, right? And so on. Imagine that it is in circles in the phi direction. That's the magnetic field, okay? Expressions, you don't need to memorize them, but the end result, because of this direction in theta and this direction of phi, when you try to figure out where is the signal propagating, or the energy of the electromagnetic wave, in which direction it is propagating, you will find that it's propagating in the direction of R. So this is how your signal travels. This is how your power transfers from one point to the other, right? So it moves in all radial directions, right? It's always going in all these directions, right? That's where your power is going out of that antenna. Then we studied actually not the power density S or the pointing vector S, but we looked at something called the normalized pattern F, and that F was equal to S divided by its maximum value. So the radiated power density, power per unit area, divided by its maximum value will give us something called the normalized radiation, or the normalized pattern of the antenna. When we plot that for the Hertzian dipole, we found that it looks like a butterfly. So it has a maximum in the direction perpendicular to the antenna in this direction, and a maximum on the other direction as well. And the plot in coordinates, in polar coordinates, looks something like this. Something like the infinity sign, right? This is how the pattern of the antenna, the maximum is in this point and this point as well. And then it gets smaller as theta increases away from normal to the antenna direction, right? What does this radiation pattern in general as a characteristic of an antenna define to us? It shows us how the antenna is concentrating the radiated power in certain directions. Now that's just showing it. If you want to get a quantitative quantity that tells you how is that compared to an antenna which is not doing the concentration, we call that the omnidirectional antenna. We found that there is a property called directivity, and that directivity defines in the direction of maximum radiation how much is the energy or the power concentration compared to an antenna which is not directional at all, which does not concentrate the energy in any direction. Okay, that was one property of the antenna. So you have a radiation pattern that tells us in different locations of space how generally the power is distributed for that antenna in terms of concentrating it in certain directions and less in other directions. And then if we want to know in the direction of maximum, in this direction, how do we compare to an antenna which is not focusing the power? Then we use a measure called the directivity of the antenna. Now, when we move to practical antennas, we start discussing something called the efficiency. If I put a certain power as an input to the antenna, how much of that gets really radiated? That's called the efficiency of the antenna. And if we multiply this efficiency by the directivity, we get something more practical that represents how much the energy is concentrated in the direction of max. And we call that the gain of the antenna, G. Okay. This is kind of a quick summary of what we did in the lecture last time. Now, today, we are going to look at more practical antennas. So we will look at an antenna which has a dimension comparable to the wavelength. That's typically what happens in our antenna designs. We don't really have Hertzian dipoles because those ones are very inefficient. They waste a lot of power. So we don't use those very, very, very small antennas. We typically use antennas with dimensions comparable to the wavelength. And in this case, we look at the dipole. Basically, the reason that we studied the Hertzian dipole because it was mathematically easier to analyze in the electromagnetic domain. You are not required to do that analysis. I remind you again, but just I want to give you an idea what's happening in this domain. And then once we analyze the Hertzian dipole, you can think of the large dipole as many of those Hertzians added one after the other. So you can imagine that we will take the analysis of the Hertzian and perform some kind of integration on it to get an expression for the electric and the magnetic field coming from an actual dipole. And the one that we will analyze here is the half wavelength dipole. That's the most efficient, yet small in size as much as possible relatively as we can go with the dipole antenna. Again, we're not really concerned about how the analysis is done. The slide is left for your own information. But what we care about is the final expressions. Again, you don't memorize them, but just understand them and what they represent. So we have here the electric field, again, for the half wavelength antenna. So the length of this antenna is equal to lambda by 2. The electric field is again in the theta direction, similar to the Hertzian dipole. And it is again a function of the input current or to the antenna, as well as the angle at which we are trying to measure the electric field. So theta is the angle at the point where we are trying to measure the electric field. And it's also a function of the distance from the center of the antenna and has the same sinusoidal dependency on the spatial domain using the complex exponential e to the minus j multiplied by k. K is 2 pi over lambda multiplied by r. Okay, so that's very similar to the one that we got for the Hertzian, but the expression here is different. This is not exactly the same. Okay. And the magnetic field, again, is in the phi direction, and it has this same expression divided by the permeability of free space, similar to what happened in the Hertzian dipole. Now, given that this is the electric and the magnetic field, you can go and calculate S, the Poynting vector, or the power density, which is the cross product of those two. And the result of that is going to be this expression. Similar to what we did there, this expression is composed of an expression in the angle theta, and then another expression, which is a bunch of constants, as well as the input current and the distance from the antenna. Since this part, which is the dependency on the input current, some constant value, and the dependency on the distance from the antenna is the same for any antenna, the same means that the dependency is the same. You always depend on the maximum input current. You always have an inverse relation to the square of the distance from the antenna, but the constants here might change from one antenna to the other. So basically, we try to omit this from what we look for, and this is why we calculate, just a reminder, this is why we calculate the normalized pattern or the normalized radiation, and that one is equal to this expression divided by the maximum value here, and you end up with the F of theta, the pattern of this antenna given by this expression. If you go and try to plot this expression as a function of theta on the polar plot again, you will get very similar butterfly shape. So maximum radiation is perpendicular to the antenna on the right and the left side. But there are differences because the beam width here is different. And we'll see later on that also the maximum value here, the directivity is also different. So the beam width here is around 78 degrees. This is the half bandwidth beam width. The beam width when the power drops to its half of its value, or 3 dB, if we use a dB scale on this one. And we will find that the directivity of this antenna calculated in this slide, you don't need to do the calculations again, but just understand that the directivity for this dipole half wavelength is equal to 1.64. Remember, for the Hertzian, it was approximately 1.5, right? So there is a difference. The dipole, the one which is half wavelength, gives better directivity, puts more concentration of the energy in the direction of maximum radiation, as compared to the Hertzian dipole antenna. Okay, now moving from dipole, which is again another impractical implementation of antennas. Typical implementation of antennas uses a monopole antenna. And a monopole antenna is composed of, if you have the two conductors of the transmission line, for example, let's say here we have a coaxial transmission line, where this is kind of the outer shell, and this is the inner conductor. So you take the outer shell and you conduct that to, or you connect that to the ground or a grounded conducting plate. And then you take the inner one and you extend it out by a wire, and the length of that wire is equal to lambda by 4. By doing this, you have formed a monopole antenna. We call that the quarter wavelength because the side here is lambda by 4. Again, if you do the electromagnetic analysis, but you are not required to do it, you probably have touched upon something called the method of image in your electromagnetics course, whether in physics 2 or the electromagnetics course. But the end result is that when you have some setup that has some conducting material close to a grounded conducting plane, then you can, the final analysis of this is equivalent to analyzing, removing this plane completely, and then considering as if this has a reflection on the other side. This is kind of like a virtual reflection, does not really exist. We call that the image. And the method of analysis that uses this called the method of image. Anyways, this tells you that this quarter wavelength is going to behave more or less like the half wavelength dipole. But it's much easier to implement because you don't have two wires going in two different directions, which is harder to implement in real life. But you have here like a grounded or conducted or shielded plane, and then another just wire going. And that's what you see in your antenna for your radio receiver at home, or the antennas used for cars, for example, when you have those mobile phones on the cars, particularly for people who work in MOI, Ministry of Interior, or whatever, you have that long antenna because they use smaller frequency or low frequency, and accordingly their wavelength is really large. So they have only one wire. You don't see two wires coming out of the car. And the reason is that they are implementing a monopole antenna, a quarter wavelength monopole antenna. Okay. So again, the analysis of this, the radiation pattern, everything for this quarter wavelength is going to be exactly the same as what we did for the dipole. Same directivity, same beam width, same analysis, same expression for the normalized radiation pattern, same shape for the radiation pattern of the antenna, but it's different implementation on the implementation side, on the actual wiring or actual hardware side. Okay. Any questions before we move on to the next topic of today? So we have discussed the dipole antenna, the radiation pattern for that dipole antenna, and the fact that practically we implement monopole antennas, not typically dipole antennas. Any questions?
Doctor, just one question. What about the antennas, the ones that were used in the old TVs, the one that have two legs?
These are two antennas. They are not dipole antennas.
Okay, perfect. Okay.
Okay. Any other question? No other questions? Okay. So this is just, it does the analysis for this dipole antenna, but using that simulation tool, so it's just left for your info, not really important. Now, I mentioned last time that we discussed in the last lecture the properties of antennas, but we left one or a couple of properties to be discussed in this lecture, in today's lecture, and the reason is this property that we will talk about today has to do with antennas that has a considerable dimension. You cannot really figure out this property for an antenna which is very, very, very small, such that you consider it without really any considerable dimension or size, right? And that was the case for the Hertzian. So the property that we'll discuss today is very important in terms of doing your analysis of communication system, and it's called the effective area of the antenna. Now, physically, what does the effective area of the antenna mean? It means actually the kind of the area that intercepts the electromagnetic wave. Imagine that your source is here, and then accordingly the radiated power coming out of this source, as we said, goes in all directions, right? So it goes this way, right? It goes this way. Sorry, it should be straight line, but just I'm trying to make it straight line, but it doesn't work very well with me. But anyways, and it goes this way, right? And then you have some of it which is intercepted by the antenna, right? By the area of the antenna from here to here, and the rest is going astray. It never catches with the antenna, right? The rest goes away and it's not captured by the antenna. Now, the effective area of the antenna is a representation of how much area is this, right? Or the ratio between this area and the area and the area of the sphere at the location of the antenna, the surface of the sphere over which all the other radiations go through. So all the other radiations on that imaginary or virtual sphere around the source, they are not captured by the receiving antenna. The receiving antenna only captures what goes through this area, right? So the ratio between what's captured and what's lost is called the effective area on the antenna. And that ratio is represented by the total power intercepted by the antenna, so Pn, the amount of power collected by this surface of the face of the antenna, divided by the power density coming from the source at this point, at the point of the antenna. So the power density S that we calculated for the antennas before, right? So if you take S in the denominator here, and you take the total power collected by the surface of the antenna, Pn, the intercepted power, you divide this by this, the result will have a dimension of area, because S is power per unit area and P is power. So watts divided by watts over meter square. So the dimension is going to be meter square, which is a dimension of area. And we call that value the effective area of the antenna. Now, how is that calculated? There is a theoretical electromagnetic analysis that you can do to do that calculation. or experimental by collecting the total power, and the S you already know it from the antenna analysis itself. So either this or that. In both cases, you can calculate that effective area given a particular antenna design. Generally speaking, for any antenna, if you do the electromagnetic analysis for any antenna shape, you will find that the effective area of the antenna is equal to lambda square multiplied by the directivity of the antenna divided by 4 pi. So A effective for any antenna is equal to lambda square multiplied by directivity divided by 4 pi. For the case of short dipole antenna, you substitute the directivity of that and you get the expression 3 lambda square over 8 pi. Okay. But in general, it's given by directivity divided by 4 pi multiplied by lambda square. That's the effective area of any antenna when it's receiving a signal from any transmitter. Okay. Now, using that effective area expression and trying to do an analysis to figure out a relation between the power input to a transmit antenna and the power received at the output of a receiving antenna, we end up in free space in propagation in areas where you do not have any reflectors. So you are not inside a building, you are not around buildings, you are not very close to the ground or earth, right? In that case, in the case that you have free space, no obstacles, nothing reflects your signal, and the transmitter is sending a signal which is being intercepted or received by a receiving antenna. The analysis that we do here is called free space propagation analysis, or they call it the freeze transmission formula. And it says that the power received here divided by the power transmitted input to the transmitter antenna is equal to the efficiency of the transmitter multiplied by the effective area of the transmitter multiplied by the efficiency of the receiver multiplied by the effective area of the receiver divided by lambda square r square. Now, this expression, if you substitute the values of AR and AT, effective area of receiver, effective area of transmitter, which is given in this slide, lambda square directivity over 4 pi. So you substitute those A's by lambda square directivity of transmitter over 4 pi and lambda square multiplied by directivity of receiver over 4 pi. And we know that efficiency times directivity will give you gain. Then you can map this expression to this expression. And that's the most commonly used one. So the gain of the transmitter multiplied by the gain of the receiver multiplied by the free space term, they call it that way, or the free space path loss term, lambda over 4 pi r, all of this is squared. Okay. Now this can be used in conjunction with the property that we studied in a couple of lectures ago, that's called sensitivity of the receiver. What's the sensitivity of the receiver? It's the minimum value for the received power coming out of the antenna that the rest of your transceiver electronics can deal with. If the power coming out of the antenna is smaller than this value, this means that the remaining electronics in your receiver will not be able to figure out the signal. The signal is going to be hidden inside the noise, and it's not going to be, it's not going to sense that there is any signal being received, and it will not be able to process that. So once we substitute in place of P received the minimum required value, the sensitivity value, and we use this formula, we know, given that we know the distance between the transmitter and the receiver, we know the properties of the transmit antenna and the properties of the receive antenna. So we can substitute all these values here. They are all known to us. And of course, we know which frequency we are working on. Then, given that we know this value as the minimum, the sensitivity, we can figure out what's the minimum required input power here. And we call that calculation power budgeting. So we try to figure out how much power I need to inject into my transmitter receiver system such that the signal at the receiver side can be analyzed. This will give me the minimum required. If I go at that minimum value or more, I'm fine or good to go. Typically, in practical system calculations and as engineers, we like to use a factor of safety. So we typically calculate this value and then we maybe double it or multiply it by 1.5 or triple it or whatever to make sure that if there are any errors in calculations or if the environment changes one way or the other, we still maintain a good communication between the transmitter and the receiver. This operation is called power budgeting, and you have studied this in your communication systems course, as well as those who took advanced communication. I think you have studied it again with more details. So up to this point, when we finished the concept of effective area and the usage of that effective area to figure out the power budgeting formula. Any questions from your side?
Yeah, what does R represent here? Like, is just the distance or
Distance.
okay.
The distance between the transmitter and the receiver.
But does this calculation not account for like the losses across the channel, or does it assume a perfect channel?
What do you mean by the losses across this channel? Because this
So,
is called already a free space path loss. So what do you mean
okay.
by the losses? Yeah.
So this is assuming free space.
Yes, exactly.
Okay.
Any other questions? So, okay, following up on the question from Mahmoud. Okay, so Mahmoud, you see this, as you said, this is the analysis in the case, and I mentioned this at the start of this slide. This is the analysis in the case that we are really dealing with a very ideal environment. For example, this applies in satellite communication because typically in satellite communication between the ground station and the satellite, there are no reflecting buildings or cars or anything, right? It's typically just a free space propagation between the ground station and the satellite. Okay. Now, what happens when we are dealing with other environment? Let's talk about Wi-Fi inside a building, or let's talk about cellular signal in the downtown or between on the streets between buildings and stuff. Of course, in this case, we have lots of reflectors, and the signal is no longer just one path from the transmitter to the receiver. But what happens is the signal can go through a reflector and arrive here, another reflector, right, and arrive here, and so on. So we have all these possibilities of what they call the multipath effect, right? So the signal comes from different directions. Is this good or bad? It can be good if all of these arrive added together with the same phase, right, or 2 pi phase shifts. But if these signals or electromagnetic waves arrives with phase shifts that causes them to destructively interfere, they will cancel each other. So the end result is that collectively for those systems, the performance is worse. It's not the free space will almost always do better performance or less losses compared to the multipath. And practically to accommodate for those multipath effects, if we are looking for path loss analysis, then typically rather than this being to the power 2, it becomes to the power 2.1, 2.3, 2.5, 3, 3.1, depending on the environment. How do we figure out that exponent? Typically done by experimental analysis. So we have a transmitter receiver, we measure the power at different times, and then we take the average of that, and then we do a curve fitting of that average that we take at the receiver side to the expression of the path loss, assuming that we don't know this. So this is going to be n. And from that curve fitting, we figure out the value of n. They call it the path loss exponent, right? So for different environment, typically this is what changes. The rest stays the same, okay? So that's, again, how you do this. And if you look it up in any of those wireless communication courses, particularly, for example, the book by Theodore Rappaport, you will find how they do that curve fitting, how they do the statistical collection of data, and then do the curve fitting. When I was teaching the wireless course a few years ago, the elective wireless course, I actually had this as one project for the students. So they go around the buildings of the engineering, the old buildings. By the way, I'm giving you the lecture now from the new building of engineering. So they go through the old building and they have measurement devices or Wi-Fi nodes, and then they calculate the RSSI, and from that received signal strength variation and calculation at different points. They do the curve fitting operation and they figure out the path loss exponent for the propagation in the engineering building. It was a very interesting project to do, but we're not going to do it in this course. It's irrelevant to the course. So now, any questions, any other questions on this before we move to the next topic?
So for here, like the way we compensate for the path losses, just changing the exponential on the
Yes.
path loss.
Yes.
Okay. So we don't need to do channel modeling, or in this case at least.
That's channel modeling.
Oh.
But again, channel modeling has many stages. We are here only looking at something called the path loss. Okay. The other stages that you are talking about are probably things like the, they call it the small scale fading variation. That's a random value added to this path loss. But that is a different analysis. Here we are only looking at, as you go away from the transmitter, how much of your power is lost, right? So it's only a distance dependent analysis, this one. Of course, in addition to types of antennas that you use and wavelength and so on, but the main characteristic here is as you go away, as you increase the distance between the transmitter and the receiver, how much you lose in terms of power on the average. This is a long-term average, okay? Any other questions? Okay. This is just an example. You should be able to read it and solve it for you by yourself. It just uses this analysis that we talked about. So I will leave it for you to look at it. It's not really difficult to understand. Now, the next topic is antenna arrays. So what is antenna arrays and why do we need to use them, or why do we need to look at them? So antenna arrays is when you, rather than using a single antenna, you start using multiple antennas in your transmitter or in your receiver. But typically those multiple antennas are organized in a certain geometric shape that has certain properties. So each one of those is called an element, as we see here. So you have an element, an element, an element. Each one of those elements can be anything. This one, for example, those elements, for example, can be a half wavelength dipole, or they can be a reflector antenna, or they can be a microstrip antenna. But you are using one microstrip antenna, another, a third, a fourth, and so on, and arranging them in a certain geometric shape. That's called an antenna array. Now, the same signal goes through all these antennas with some modifications in the middle. If each antenna is receiving a different signal, that's a different topic. It's outside what we are looking at here. That's called the MIMO, the multi-input, multi-output system. Or if that happens both at the transmitter and the receiver, then it's called MIMO. If that happens at the transmitter only and the receiver has a single antenna, it's called MISO, and so on, right? So that multi-input, multi-output, it's different from the antenna arrays. The main difference is, rather than being one single signal, one piece of information that's being transmitted over all the antennas, but with some modifications here, and I will talk about those modifications in a minute. In this case, this is called an antenna array, okay? Now, if I have different information branches, each one of them is going through a different antenna, then in this case, we call that a MIMO, multi-input, multi-output system. What we are looking at here is the same signal going through all the antenna elements, but with some variation in their amplitudes and some phase shift introduced to each one going to each element. So the signal comes from here, it's the same, but then we take the signal that goes through this one, we introduce a epsilon1 phase shift, and we multiply it by a factor A1. So amplitude variation and some phase shift, and then it gets to the output. The same signal here with another phase shift, another amplitude scaling goes to the other antenna element, and so on. The antenna arrays that we are looking at always assumes that the same element type is used in all these. So this is a dipole, this is a dipole, this is a dipole, this is a dipole, and so on. Or this is a monopole, and so on. Or this is a microstrip antenna with certain dimensions, the same microstrip antenna with certain dimensions, the same microstrip with the same dimensions, and so on, okay? So the elements themselves, they are always the same. In this case, the most common example for this is actually the TV antenna. You have dipoles, right? And there is an array of them, right? You see, remember those ones that used to be put on the ceiling of, or the roofs of different buildings, right? To receive TV signal. That's an example of an antenna array. Now, in case you do this, you arrange the antennas in a particular array, the output, when you calculate the power density coming out of the whole array at any point, this is going to be effectively equivalent to the power density coming from a single element, For example, if this is the dipole, then you use the expression that we got for S for the dipole, okay, multiplied by something called the array factor. And the array factor is an expression that depends on how you arrange them geometrically in space. The expression that we see here is for a particular arrangement called the uniform linear array. In the case of uniform linear array, the antennas are arranged over a straight line. So all the elements of the antenna are on a straight line, and the distances between them are all equal. We call that distance value D. So the distance between this antenna and the next one is the same between this and the next one, same between this and the next one, and so on. All of them are separated by the same distance. That's why we call it uniform, and we call it linear because they are arranged on a line. So for a uniform linear array, the array factor expression is what we see here, the summation of the summation here is over the elements. So I is the index, element 0, element 1, up to element n minus 1, assuming that I have n elements array, okay? And then the gain multiply. So this is the gain factor multiplied by the first element, and then the gain factor, sorry, the A0, the gain factor multiplied by the first element, A1, gain factor multiplied by second element, and so on, multiplied by e to the j, phase of the first element, phase of the second element, and so on, multiplied by the, this is the wave propagation sinusoidal expression in space. So e to the power j, j is root minus 1, I is this same index, so this changes from one element to the other, and then k is 2 pi over lambda, d is the distance between one element and the other, and theta is the angle at which my point exists. So I'm trying to calculate the value of the total power density at a certain angle theta. This is the theta that I see here in this expression. Okay, so if I go to this point, I'm at a different theta. If I go to this point, this is my theta, and so on. So it depends on the location where you are trying to calculate the radiation pattern. So in order to get the power density for antenna array, you use the power density of the single element, depending on what type of single element you are using in that array, and then you multiply that by the array factor. For the case of uniform linear array, this is the expression of the array factor. So this is what you compensate here. Okay? And by doing this, you should be able to get the total power density at any point, and then again, you can express that as maximum value multiplied by the power density, and you normalize that so you can get the F at any location. Okay. Now, this is the general expression for the array factor for the case of uniform linear array. Now, if those uniform linear arrays are all using the same phase, so there is no phase shift difference between one element and the other, so all these epsilons are the same and consider them equal to 0, then this simplifies to this expression. By the way, the gamma here is just like a shortcut for kd cosine theta. So gamma that you see here is simply k multiplied by d multiplied by cosine theta. Okay. And further, if they all have the same magnitude, so if you go here, all of these are equal to each other and maybe say equal to 1, for example, so we don't really scale them differently, then the expression becomes even simpler. It becomes sine square n, n is the number of the elements, multiplied by gamma, gamma again is kd cosine theta divided by 2 over sine square gamma over 2. Okay, this is the case for the uniform linear array, same phase shift and same amplitude. So it doesn't have any amplitude scaling, and it doesn't have any phase shifting between one element and the other. Okay, if you plot this, if you try to plot this in a polar plot, you will see the pattern that we see here. Notice that using, for example, a dipole antenna, remember the dipole antenna, how the pattern looked like. I will draw it here just to remind you. Let's do it with some light color. Hopefully it's light. So this is how it looks like, right? And there is a similar one on the other direction as well, right? Now, remember, the total radiation, this plot that you see with blue is actually the array factor, right? And then the plot that you see with yellow is the S of the dipole antenna. When you multiply those together, you will notice that this side will disappear because it's multiplied by 0. There is no, the array factor on this side is all equal to 0. So this yellow side here on the left side will be multiplied by 0. So it will disappear. And then the shape here is going to change slightly, but still it will have something like a main loop and then other side loops that are smaller because of the scaling at this point, right? So smaller side loop, right? Now you can see that using an array of antenna, we can achieve something which is almost impossible to achieve using a single antenna element. For example, here, we can make sure that the power is radiated only in one direction. It doesn't go in the other direction, right? And not only that, we can also get some side lobes. Sometimes these are desired, especially if they are not much smaller. And if you look at some antenna designs, you will see that this might be desired so that you can communicate to two receivers at the same time, for example, okay? So that's why we use antenna arrays, because we can achieve some properties of the radiation pattern, which are difficult to achieve with a single antenna design, no matter what we do with the antenna design. One thing to keep in mind is that typically for those array patterns or array factors that we see, the number of zeros, the number of depths here is directly related to the number of elements. So if you have n elements, then it's n or n minus 1, depending whether n is even or odd, right? The number of zeros that you encounter, right? So basically, introducing more elements means that you know immediately that you will have more of those side lobes because you will have more zeros and then you will have more side lobes. That's something to keep in mind when you are doing the design of the array. Okay. This is again another example solved for the array factor calculation. So it tells you that you have a two elements array represented by those red dots, right? And they are separated by a distance 7 lambda over 2. So n is equal to 2, capital N is equal to 2, and d is equal to 7 lambda over 2. That's the distance between the two elements. And it asks you for this particular configuration, what is the array factor? So regardless of the antenna itself, just you need to calculate FA, the array factor. Apply the same rule that we mentioned. And it says here that they are equal excitations. So this means that there is no phase shift and there is no amplitude scaling. So you can consider the case where all the A's are equal to 1 and the phase shifts all are equal to 0. And this is why you end up with, when you try to solve this expression, you end up with 1 plus e to the j gamma, right? Those two terms inside the square. Now, if you can substitute the e to the j gamma with cosine gamma plus j sine gamma in this expression, you should be able to figure out, to come up with this result, that the array factor for these two elements is equal to 4 cosine square gamma over 2. What's gamma? Gamma is k multiplied by d multiplied by cosine theta. K is 2 pi over lambda multiplied by d multiplied by cosine theta. That's gamma. Okay. And then if you try to plot this in a polar plot, you should get this figure that you see here for the this particular array of two antennas. Any questions?
Doctor?
Yes.
Shouldn't we have a main lobe at least one? Here I can't find or recognize the main lobe.
You cannot, mafish main lobe. In this is for this array factor, there is no main lobe for this particular one. They are all the same size.
Okay, so there's a possibility there multiple antennas.
Yes, but always we call for the uniform linear array, we always call the one in the direction perpendicular to the array arrangement. So you see the array arrangement is in this direction, right? Okay, the one lobe perpendicular to that, we call that the broad side, or sometimes they call it the main lobe. But again, don't forget, this is not the actual radiation pattern. This is only the array factor pattern. Still, this has to be multiplied by the antenna pattern itself to get the actual output pattern. Okay, so for the array factor pattern, the lobe or the beam in the direction of 90 degrees perpendicular to the arrangement of the array itself, this is called the broadside, okay? But still, in this case, for example, we don't have a particular gain in the broadside as compared to the other sides.
Yeah, okay, thank you.
So, Doctor, here if we're using a monopole antenna or a dipole antenna, we usually won't have any lobes other than the broadside, since the other ones would be multiplied by 0, right?
لا.
Since
If you use, for example, let's say we are using the monopole or the dipole, how does it look like? The pattern بتاع المونopole or dipole, it looks like this, right?
yes,
And then in the other side also we have similar. The other side is going to be multiplied by 0, فخلاص. The collective result of this multiplied by those is going to be, this lobe is going to stay very high because it's multiplied by approximately very high value here, right?
okay,
This lobe, right, is going to be smaller because it's multiplied typically in this range, it's multiplied by those values, right? So you'll have something like a smaller loop here. And then this one is going to be smaller. And then this one is going to be even smaller. صح?
okay,
And
yeah.
you need to multiply this value with all those values that you see here. صح? Yeah, so that's why you will end up, when you incorporate the actual antenna power density, you will end up with clear main lobe and other side lobes. What the blue line says is that for this arrangement of array, تمام, you don't really have a differentiation between the broadside and the other sides in terms of the maximum value. They all reach the same maximum value. However, when you incorporate this array arrangement with a particular antenna, you might end up with a clear main lobe and other side lobes. تمام؟
تمام. شكرا دكتور.
Doctor, regarding the number of zeros, it's proportional to the number of elements, right? Not equal to.
Yes.
Okay, thank you.
Other questions? Right. Last topic that we'll discuss today is going to be related to, now imagine, for example, let's first kind of, okay, after doing the multiplication of those two, we end up with something like this. Okay, so we have this main loop, maybe we have a side loop here, another one here, side loop on the other side, another small one, and that's it. Okay, so that's our radiation pattern, and the maximum coming out of the antenna is in this direction. معلش افترضوا ان هو in this direction. Okay, and in all other directions I have less power and even less and even less and so on. تمام? Okay, now imagine that this is my transmitter and my receiver is here. So let's use a better color. So my receiver is here. I should be fine because my receiver is going to receive the maximum power. Now imagine that at some point my receiver comes to be here. Again, if I leave the setup as it is, then this receiver is going to receive something attenuated, right? These values are attenuated values. So it will receive much less power compared to when it was here. Now, in order to overcome this problem, I need to make sure that I tilt the beam so that the maximum goes to my receiver. Now I can do this typically by taking the antenna array and rotating it, right? Tilting it until this maximum becomes in this direction. This is called mechanically steering. So my antenna is going to rotate to try to track the receiver, to try to make sure that the receiver, when it is moving, my maximum radiation still goes to the direction of the receiver. صح كده يا شباب? This is called mechanical steering. I'm steering the beam, the maximum value, to be always pointing in the direction of the receiver. How do I do that? I rotate the antenna array كلها. But when I rotate the antenna array, this whole figure rotates with it. تمام? Okay, that's one way to do it. Now this is not always practical for many reasons. منها ان mechanical system have reliability and maintenance issues. منها ان mechanical systems are sometimes they are slow because they have inertia, والantennas دي particularly if we talk about a base station antenna, they are heavy, so you cannot really steer them very quickly, fast enough to track a fast-moving receiver and so on. So there are advantages to mechanical steering. Okay, what is the other option? The other option is called electronic steering. How do you do electronic steering? If you go back to the expression of the linear array, this expression, right? For the array, the general one, or even let's use the simpler one, the one that has, no, we cannot use this one. We'll use the general one. If you look at the general expression here, you will notice that, okay, depending on this distance d, as well as the phase shift that we have here, we can actually control in which direction the maximum is going to happen. And if you do the math and the calculation, you will find that if you want, for example, your main loop to be in a direction called theta naught, so if you want the maximum to be in this direction, and this direction from the Z angle is theta naught, okay, then you go and calculate the phase shift between one element and the other, call it delta, to be equal to K multiplied by D, the distance between the element, multiplied by cosine, that angle that you want the maximum to be in. Okay, and then you make sure that for the first element, there is no phase shift. Second element, you put a delta as a phase shift. Third element, you put double that value. Fourth element, you put four times that value. N element, you put n times n minus 1 times that value, right? So you move with fixed phase shift between one and the other equal to a value of delta. Delta, 2 delta, 3 delta, 4 delta, 5 delta, and so on. Okay. If you do that, given that you have calculated delta to be this expression, you will find that the pattern of your antenna is going to change such that the main loop is going to be in the direction of theta naught that you used in your calculation. Okay. This means that this is effectively equivalent to when you take the antenna array and you rotate it, right? But now you are not doing it mechanically. You are just doing it by controlling those phase shift elements to be equal to multiples of this value as we represent here in sequence, delta, 2 delta, 3 delta, and so on, where the delta is equal to this expression. Okay. Now there is a disadvantage to this. So the advantage is no longer you need mechanical steering. The disadvantage is when you use electronic steering, you start losing the beam sharpness. So as you go away from the broadside, from the original location of the maximum, as you go away from that, you increase the angle theta naught that you want the maximum to go to, your main beam becomes wider. You see here the green one is wider than the red one. And if you go to the blue one, which is 90 degrees shifted from the broadside, it becomes even much wider. Why having the beam wider is something not desired? Because even though the maximum is going in this direction, but you can see that your receiver is not going to only receive the maximum, it's going to receive the maximum plus some values around it due to its effective area. And accordingly, it will not receive most of the power concentrated close to the maximum. You will lose a little bit of the efficiency because the beam is wider. So some of that radiated power is going to go away, will not be captured by the effective area of the antenna. Okay, that's called electronic steering of beam instead of doing the mechanical steering. Advantage is you can do it easily, quickly, because this is done by using some digital signal processing techniques that can do the steering very quickly and very cheaply compared to mechanical element. Does not require that much maintenance as compared to the mechanical. However, the disadvantage is you have some losses in terms of getting a wider beam a little bit. So your beam becomes wider when you are steering away from the broadside. Any questions about electronic beam steering?
Doctor, can you move back to the previous slide? Yeah, the angle, is it delta or theta naught?
No. The angle in terms of direction is theta naught. Delta hena is the angle in terms of phase shift between one and the other. يعني الدلتا هنا، الدلتا that you see here تمام is the representation of this psi. Remember there is a psi, right? There is a psi phase shift for each element. تمام. That psi becomes delta. So that's an angle in terms of phase shift. ملهاش علاقة بالactual spatial angle where the maximum direction is going to be. مش ملهاش علاقة. It's not the same. The relation between them is this. تمام. So this delta is your induced phase shift. This theta naught is the direction where you will have the maximum, where you want the maximum to be. Clear كده?
Yes, no, it's clear. Thank you.
Any other questions?
Doctor, can you please repeat the part about the disadvantage? Like
About
you
it?
receive the signal, like when the beam shape becomes wider, you will receive the signal. You said plus something.
No, I didn't say plus something. I said you lose some of the power that you receive. Because again, narrower beam means most of the power is concentrated in very small area, right? Wider beam means that the power is spreading across larger area. When you receive only according to the area of your receiving antenna. So if most of the power is concentrated in a small area, this means that the area of your antenna is going to capture most of the power. If it's spread on a wider angle, this means that your antenna will capture some of it, but the others are going to escape, right? So this means that the efficiency of your reception of the power is going to be a little bit less.
Okay, clear.
Yeah. Other questions يا شباب? طيب, we are at the end. So this is a summary of what we did in both lectures. Some of it is like the solid angle and those kind of not, remember I told you the solid angle is not something very important, but at least it summarizes for you all the properties that we have studied when we looked at the Hertzian or the short dipole as opposed to the lambda by 2 or the lambda by 4 monopole, the propagation expression, the principle when we deal with antenna arrays and how to represent that in 2 stages if you want to get the power density and so on. Now, so this summarizes basically what we have been through through those 2 lectures on antennas. And just from my point of view, what I want you as RF engineers to keep in mind, again, you are not going to be designing antennas per se, because that's a different job. Designing antennas is not typically the job of RF engineers, but it's more of people whom they call antenna designers. They deal a little bit more with electromagnetics and simulation tools from electromagnetics field. But as RF engineers, you need to understand the effect of the antenna and its characteristics on your communication system. And you need to be able to read data sheets for antennas, figure out how to select a particular antenna that fulfills your communication system requirements, understand that when you look at the antenna pattern, you know exactly how the power is distributed in spatial or in the space. So you know where to place your transmitters and receivers to be able to efficiently retrieve most of your signal. And also when you look at the directivity, this gives you a qualitative or basically the more practical one, the gain. This gives you a measure of how good this antenna in terms of concentrating the energy in the direction of maximum radiation. And accordingly, this helps you with the design. You take those factors, you can plug them into the power budgeting equation to do some kind of analysis. How much power do I need to inject in the transmitter in order for the receiver to be able to process the signal, or in order to receive at least the sensitivity amount at the receiver side. And then accordingly, this can affect your power amplifier design, your quality of your electronics, if you want to make sure that you receive lower power signals and so on. So basically, antennas, you are not going to design them, but part of you designing your system, you are going to choose one of those antennas, and you need to be able to read their data sheets, understand what their characteristics means, so that you can actually choose the right antenna for your communication system design. That was the objective of going through this whole part. If there are no more questions, I'm going to stop the recording and go to the attendance. If there are questions, I'm willing to receive them before doing so. I'm not reading the text, so if anyone wants to ask, please open your mic and ask. I cannot see the text here. No questions?
Doctor,
Yes.
can we have this week recordings?